All right, so we want to sketch it, so we're going to look at our first derivatives and our second derivatives. F prime of x, 3x squared minus 6x minus 9. So we make that equal to 0. You could factor out a 3 just to make your factoring easier. X minus 3x plus 1, so x equals 3 and x equals minus 1 are the points where our first derivative is equal to 0. So let's see what kind of stationary points we have. Minus 1 and 3. When we plug in a number less than negative 1, and again I'm going to use my factored thing here because then I'm going to get a negative number times a negative number times, well, 3 is always positive, which will be positive. So this part is increasing. If I plug in 0, I'm going to get a negative times a positive. And if I plug in a number larger than 3, all of those will be positive. So it's increasing. So we know that negative 1 comma something is going to be a local max. And we know that 3 comma something is going to be a local min. If we want to find out exactly where they are, we got to plug those points back into our original function. So we're going to have negative 1 minus 3 is negative 4 plus 9 is 5 plus 1 is 6. Is that right? Yeah. And when we plug in 3, we're going to get 27 minus 27 plus 1 is negative 26. Yes? All right. So now we've got our local max and our local min. I'm going to start my second derivative over here. I'm going to use that non-factored form because that will be easier. We get 6x minus 6. Make that equal to 0. Now, I'm curious right now. How many people solve this by factoring, and how many people solve this by moving the 6 over and dividing by 6? Okay, so moving the 6 over and dividing by 6. And who factored? Isn't that neat? Because, I mean, when you think of this, that's back to grade 9. You would have, for so long, you just isolate x, right, and divide and get x equals 1. But we've been factoring so much that you ended up solving it by factoring. I just think that's kind of neat. It's not wrong to take out a 6 and get x minus 1 and go, oh, x equals 1. That's also right. Just two different ways of seeing it. But you would never think of doing this until now. But just the way your brain has kind of been trained by looking at these questions. So now we got 1. Sorry, we've got 1. 1 isn't one of our local mins or our local maxes. And if we check a number less than 1 into this, like negative 5, we'll get a negative number. So this is concave down. And if we check after 1, we'll get a positive number, which is concave up. Draw our little cyclopses there. And we now know that 1 comma something is an inflection point. And if we plug in 1, we're going to get 1 minus 3 is negative 2, minus 9 is negative 11, plus 1 is negative 10. So now we can take all the information that we've gotten and draw a pretty accurate sketch. So we're going to have negative 1 comma 6. I'm going to put that about there. 3 comma negative 26. So if that's 6, it'll be about there. Again, you don't have to be perfect in your drawing, but the scale should be reasonable. Okay, so I tried to match up whatever I used as a length of 6, kind of to try and match it up to a length of negative 26. And 1 negative 10, that's my inflection point. That would be, yeah, about there. So now when I go to graph this, when I go to draw it, I'm going to start from my inflection point. Okay? Another point that we could figure out from here easily is our y-intercept. It's not hard to plug in 0 for x and to see that we would have a y-intercept at 0, 1. So I'm going to put that. What's that? It says it in the original equation? Yeah, I mean, it's easy to see it from the equation. So that's why it's worthwhile to put that point on our graph as well. And x-intercepts and y-intercepts often hold a lot of meaning, so when you can draw them in, we will. Okay? This one at the beginning doesn't factor nicely, so we can't find its x-intercepts nicely. So what I'm going to do is I'm going to start from my inflection point. I know to the left it's concave down, so I can draw that part concave down. And to the right of it, it's concave up. And we get a nice looking x cubed graph in the end. Okay? I find that if I try to draw the whole thing at once, when I hit my concavity point, I end up not changing concavity exactly there. It's hard to do that. But if you start from that point and think about concave up and concave down, it makes it a little bit easier.